Then today I want to begin section 3.4, which is about vector equation and parametric equation for lines and planes. So far we have learned how to write an equation for a line in R2. So in R2, if you have a line that passes through let's say x0, y0 and is orthogonal to the normal vector AB, yes, a line like this, we know how to write a point normal equation for that, and that point normal equation is going to be a times x minus x0 plus b times y minus y0 equals 0. But what if we have a line in R3? What if we have a line in R4? Generally, how do you write an equation for a line in Rn? This point normal equation works only for a line in R2. It doesn't work for a line in R3 or R4 or any other higher dimension. So as you can see, the point normal equation for a line is very limited. We also learned about in R3, if you have a plane that passes through, let's say, the point x0, y0, z0, and is orthogonal to the normal vector ABC, we figured out a point normal equation for that. It has the form a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. Basically, we use orthogonality to figure out these formulas. But again, as you can see, this is also limited, because what if you have a plane in R4? What if you have a plane in R5? How do you represent a plane in a higher dimensional space? These point normal equations, they only work for line in R2 and plane in R3. If you want to represent a line in a higher dimension or a plane in a higher dimension than 3, then you need something called vector equations. Vector equation for lines and planes, or parametric equations, which is equivalent to the vector equations. They just look a little different. And this would be the topic of the class today. 3.4 is about vector and parametric equations for lines and for planes. I think I'm going to cover this lecture in 2 parts, half of it today, the next half next class. Today, I would like to talk about lines, and then next class, we talk about planes. So in this section, we will learn how to represent lines and planes in Rn using vector and parametric equations. This will enable us to view the solution set of a linear system in n unknowns as a geometric object in Rn. So you must remember the general parametric solutions for linear systems. After we have studied vector and parametric equations, you will see a similarity. You will see actually that the general parametric solution is actually a vector or a parametric equation of some geometric object, which could be a line or a plane. So this will also help you view the solution set of a linear system as a geometric object in Rn. Okay, so vector and parametric equations for a line. In Rn, a unique line is completely specified by a point P0 on the line and a non-zero vector V parallel to the line. So let me make this clear. Imagine I give you this point, and I call that P0. And for the sake of simplicity, imagine that P0 is a point from R2, and we are just dealing with a line in R2. And I give you this vector. I'm going to call that V. And I say, draw the line that passes through P0 and is parallel to V. Then there you have only one choice. There is only one line that's going to be through the point P0 and also parallel to the vector V. There is no disagreement on that. There is only unique way, one way to do that. Now, imagine R3. If we are in the three-dimensional space, the real world, and I ask you, think of the line or imagine the line that passes through this certain point and is parallel to this certain vector, then there is only a unique way you can imagine that. So what does that tell us? That tells us these two pieces of information, a point from the line and a vector parallel to the line, they completely and they fully specify, they fully describe a line in any space. Could be R2, R3, R4, whatever. Is that clear? Now, any point that is on this line, so think of, for example, this point, let's say the arbitrary point xy on the line. Then I can create a vector that goes from P0 to P, the vector P0 to P. And you would agree that P0, P, this vector, is parallel to the vector V if and only if P is part of the line. So for any point on the line, the vector P0P will be parallel to V, and for any point that is outside the line, then P0P will not be parallel to V. So I can say that P0P is parallel to V if and only if P belongs to the line. So that gives us an equation for the line, because two vectors are parallel if and only if one of them is a scalar multiple of the other one. So in other words, I can say P0P must be some scalar t times V. But also notice that P0P is terminal minus initial. It's terminal minus initial. So I can write this as OP minus OP0. This is the vector that goes from the origin to P minus the vector that goes from the origin to P0. Terminal minus initial is equal to TV. Now, just moving this to the other side, I get OP is OP0 plus TV, where T is any real number, any scalar, and that can serve as an equation for the line that passes through the point P0 and is parallel to the vector V. So let L be a line in Rn that contains the point P0 and is parallel to the non-zero vector V. Of course, V shouldn't be the zero vector because it's supposed to give us a direction. Then the vector equation, as you can see, this is a vector equation. OP is equal OP0 plus TV represents the line L. And it simply comes from the idea that any vector inside this line is going to be parallel to V. And two vectors are parallel if and only if one of them is a scalar multiple of the other one. It's only these two simple ideas. Now you might say that I am used to the idea of representing lines as points. A line is a collection of points, or generally a curve is a collection of points. How come this vector equation can represent a line? There is a correspondence between lines and vectors. So here we can take the vector OP to be equivalent to the point P. Because if I put a vector in the standard position, let's say, for example, this vector, this is O, this is P, and let's just imagine that it passes through the point, it is the vector OP is, let's say 5, 5, 2, 5, 3. Yes. What about the point P? The point P would be the point 5, 3. So you can see that there is a correspondence between the vector OP in the standard position and the point P, which is going to be the terminal point of the vector. They're going to be the same. The coordinates of the point are going to be the same as the components of the vector, as long as the vector is in a standard position. So we're using this. Here, we are representing the line as a bunch of vectors. Yes, so it's like this. This line here is represented as all the vectors that go from O to a point on the line. Is the idea clear? So again, I'm going to emphasize that here we take the vector OP to be equivalent to the point P. Then this collection of vectors can represent the line, because each vector is now equivalent to a point. Particularly in R3, if you have a line that passes through this point, x0, y0, z0, and is parallel to this vector, v1, v2, v3, then this vector equation becomes x, y, z is p0, op0. That's going to be x0, y0, z0 plus tv. So t, v is going to be v1, v2, v3. What is this? This is called a vector equation of the line. This is a vector equation of the line that passes through this point and is parallel to this vector. Now, you can see that this is equivalent to saying that x is x0 plus t v1, and y is y0 plus t v2, and z is z0 plus t v3. Yeah, so if you just make the components equal, x has to be x0 plus t v1, then y has to be y0 plus t v2, and z has to be z0 plus t v3. Yes, so you can see that these two are equivalent, but they have different names. This one would be called the parametric equation of a line. So this one is called parametric equations of the line. So if I give you the vector equation of the line, you can easily write the parametric equations of the line, and vice versa. They're basically the same thing, just two different ways of representing the same line. So equivalently, we have this, can be used to represent the same line. This set of equations is called parametric equations. So if I say, give me the vector equation of the line, I mean this one. If I say, give me the parametric equations of the line, I mean this representation. Any questions? Okay, now let's look at some examples. Find a vector and parametric equations for for the line passing through this point and is parallel to this vector. So we want both type of equation, vector and parametric, for the line that passes through the point P0, 1, 3, and is parallel to the vector -1, 5. So we're going to just use the formula O for line. OP is OP0 plus TV. So where T is any real number. So it's going to be X, Y, that's the OP, because this is from R2. OP0, if the point P0 is this point, then the vector OP0 is going to be the same thing. So 1, 3 plus T, V, what is V? -1, 5. That's it. That is the vector equation of the line. If I want to represent that as a set of parametric equations, I get X is equal 1 minus T, 1 minus 1T, and Y is 3 plus 5T. That's it, where T is a real number. So this one is called the parametric equations for the same line. Is that clear? Part B. Find a vector and parametric equations for the line that passes through this point and is parallel to this vector here. It's exact same formula. It doesn't matter whether you're dealing with a line in R3 or R4 or R2, doesn't matter. You're going to use the same formula. In this case, I can tell from the point and from the vector that this is R3. So the equation of the line is going to be X, Y, Z is equal OP0, 5, 7, 2 plus T, V. In this case, V is 4, 0, minus 1. And I hope you realize that this is the same thing as it's the same thing as those general parametric solutions when we were using the Gaussian elimination or the Gauss-Jordan. We would get something like this as the general parametric solution. So if you had only one free variable, you had only one parameter, you would get something like this. For a system of linear equations with 3 unknowns, you would get a general parametric solution like this. And now you can make the connection that actually, for example, if you have 2 planes and these 2 planes, they meet, if they're not parallel, they're going to meet at one line. Yes. And so the solution space of that linear system is going to be a line. So that general parametric solutions that we used to provide for a linear system, those are basically geometrically, they could be lines or planes or other geometric shapes. Let's do part C. Write the vector and parametric equations. Oh, I'm not done with this one yet because I also need to write the parametric equations. It's going to be very easy. X is 5 plus 4t. Y is 7 plus 0 times t, which I can only write as y equals 7. And z is equal to minus t. So this, where t is a real number, it's a parameter. So this would be the set of parametric equations for the same line. Is that clear? Okay. Now let's do that for R4. No difference here. OP0 OP is OP0 plus TV, where T is a real number. As long as it's a line, it doesn't matter whether it's R2, R3, R4, it's the same formula. So for part C, we are dealing with a line that passes through the origin. So I can take P0 to be 0, 0, 0, the origin. And it is parallel to this vector. So I have to put 0, 0, 0, 0. It's R4. So OP is going to be 0, 0, 0, 0 plus T times V, 5, 6, -1, -4. So as you can see, this part doesn't matter. So I can just say that this is equal T 5, 6, -1, -4, where T is a parameter, belongs to the real number line. And if I want to write the parametric equations, X would be 5T, Y would be 6T, Z would be minus T, and I can use W for the last coordinate, minus 4T, where T is a real number. So this one would be the set of parametric equations for the same line, and this one would be the vector equation for the line in part C here. Any questions? Okay, so part A was a line in R2, part B was a line in R3, part C was a line in R4, and you can see that there is no difference. For all of them, we are using the same formula. But for a line in R2, we are also able to express that in the point normal form. So part D of this example is asking us find a point normal equation for a line, for the line in part A. Okay. So we have a line that passes through the point P0, 1, 3, and is parallel to the vector -1, 5. In order to be able to write a point normal equation for a line in R2, we need a point, which we already have, and we need a normal. But what is a normal? A normal is a vector that is orthogonal to the line. This vector that is given here is not orthogonal to the line, it's parallel to the line. However, we can easily find a vector that is orthogonal to the line. So if you are in R2, let's say this is the line and this is the vector given, and you want to find a vector that is orthogonal to the line, then these two vectors, let's say this is V, which is given, and this is N, which we are trying to figure out. These two vectors are going to be orthogonal, right? If they are orthogonal, that means their dot product is going to be 0. Can you think of a vector that would be orthogonal to this? You just need a vector so that when you multiply them using the dot product, you get 0. What should that be? What is the most obvious answer to this? Come on, guys, it's very simple. Pardon me? Okay. 5, 1. If I multiply V and N, what do I get? I get -1 times 5 plus 5 times 1. That's going to be negative 5 plus 5. That's going to be 0, right? That makes V and N orthogonal to each other, perpendicular to each other. So I'm going to use this. I can use N, 5, 1 as a vector that is orthogonal to the given line. So this is the point on the line. This is the vector orthogonal to the line. The equation is going to be this. So I just plug in 5 times x minus 1 plus 1 times y minus 3 is equal to 0. I get 5x minus 5 plus y minus 3 is equal to 0. I get 5x plus y is equal to 8. So that would be the answer to part D. Is everything clear? Okay. Next example, find a vector equation for this line. So you can see that if I'm given a point and a parallel vector, I can easily write the vector equation for that line, and I can also write the point normal equation for that line. What about the other way? If I'm given the point normal equation, can I find a vector equation for the line? I should be able to do that. So let's do it. That's the next example here. So you have the point normal equation, 2x minus 3y is equal to 5. That means you can easily get any point from this line. And if I just plug in, for example, 1 for x, I get negative 1. For y, that could serve as P0, that is on the line. And I can see the normal vector is 2 minus 3. So in order to write the vector equation, I need P0 and I need V, which is parallel to the line. I have a vector that is orthogonal to the line. I am looking for a vector that's parallel to the line. Can anybody tell me what V should be? Or what is the most obvious form for V? If this is orthogonal to the line, can you think of a vector that's parallel to the line? You only need to think of a vector so that V times N using the dot product is 0.
3, 2.
Again?
3, 2.
3, 2 will work. This would be the vector that's parallel to the line. And this, I can use this point. The formula is going to be OP is OP0 plus TV. So it's XY is equal 1 negative 1 plus TV. So T, what about V? I can use this 3, 2. That would be the vector equation. And for the parametric equation, I can use the same thing, just separate the x and the y. X is going to be 1 plus 3t, and y is going to be negative 1 plus 2t. So this would be a vector equation for the line. This would be a set of parametric equations for the line. And this representation here is the point normal equation for the same line. See, they look different, but all of them represent the same idea. It's a bunch of points, actually infinitely many points that form a line in R2. So that was one way of getting these two equations from this one. There is another way of doing that. I'm going to show you the other way as well. So I'm going to keep this one because you will see that they look different, but I will prove to you that they are the same set of points. So the equation of the line is 2x minus 3y is equal 5. Imagine I ask you to solve this as a system. If this was a system, what would you do? Imagine this is just a system of two unknowns, x and y, with only one equation. Then this is something that we learned in the very first class. You have to isolate one of the variables. Your leading variable in this case would be x. So you isolate that. You get 2x is equal 3y plus 5. That means x is 3 over 2y plus 5 over 2. And then you would assign a parameter to your other variable. In this case, y is going to be your free variable. So it will have the form x is equal 3 over 2t plus 5 over 2, and then y is t. And the same set of equations I can write as this. 5 over 2, 0 plus t 3 over 2, 1. So now if you go back, x is supposed to be 3 over 2t plus 5 over 2, it is. And y is supposed to be t, so it's 0 plus 1 times t. That's the same thing. So this is the vector equation for the given line. And this here is the set of parametric equations for the same line. So as you can see, the vector equations, they look different. So here we have this point, here we have this other point, here we have the vector 3, 2, here we have 3 over 2 and 1. They look different, but I want to show you that these are the same thing. Because when you're dealing with a line, and you represent that as a vector equation like OP equal OP0 plus TV, then any vector that is parallel to the line, for example, this vector here, or this one, or this one, or this one, or this one, any vector that is parallel to the line and any point on the line can serve as the P0 and the V. Yes. So for example, if I'm using this point as P0 and this vector, it gives me one vector equation. If I'm using this other point P0 and this other vector, it will give me a different looking vector. Make sense? So the vector equations, they may look different, but they're going to be the same set of points. They're going to be the same set of the same bag of points or collection of points. And I can show you that by eliminating the t. So let's just try that. So this is one set that I found. I found x is 1 plus 3t and y is negative 1 plus 2t. And the other set that I found, I erased it, but I can do it in my head. Paper. No, it was 3 over 2t plus 5 over 2 and t. Okay, so I'm just trying to show that these two parametric equations, even though they look different, they are the same set of vectors. I can show you that if I try to eliminate t. So imagine if I want to eliminate t for these two. I would multiply the first row, the first equation, by -6, and I would get, sorry, by -2. If I multiply both sides of this equation by -2, I get -2x is equal -2 minus 6t, right? And I can multiply both sides of this equation by 3. So I get 3y is equal -3 plus 6t. And now if I add up the two sides, I get -2x plus 3y is equal, these two cancel out, -5. And if I multiply both sides of this by -1, I get 2x minus 3y is equal 5. So I get the equation that I began with. Yes, 2x minus 3y is equal 5. Now, what if I do the same thing with the other set? In order to eliminate t, I would just keep y as it is, but I would multiply the first equation here by -2/3. So -2/3 times the first equation. It will give me -2/3x is equal -2/3 times 3/2 is -t plus -2/3 times 5/2. And then for y equal t, I don't change anything. I'm trying to eliminate t. Now, if I add up both sides, the t and the minus t will cancel out. I get -2/3x is equal, on this side I get -10/6. Plus y is equal -10/6. Or I can also simplify that to -2/3x plus y is equal to a -5/3. Now, if I multiply both sides by 3, I get -2x plus 3y is equal -5. And then by a -1, I get 2x minus 3y is equal 5. I get exact same equation. So just wanted to try to show you that these parametric equations, when you write parametric equations for the same line, they may look different depending on what P0 you pick or what parallel vector you pick. It may look different, but as long as you're using a point on the line and a vector parallel to the line, and there are infinitely many of them, you will come up with a valid set of parametric equations for the line. And if you eliminate t, you will see that they give you the same line. Okay, so next example, it says, find a vector equation for the line of intersection between these two planes. So we have this plane, x plus 2y minus 3z is equal to, and 2x plus 3y minus z is equal 8. So if you use your imagination, you can see that for any two planes that are distinct planes and not parallel, they will intersect at a line. And if you're solving a system of equations like this one, two planes that are not parallel, and they're not the same plane, they are distinct planes, they will meet at a line. And your general parametric solution, which is the solution to the system, is going to be a line. Yes. So for a problem like this, which says find a vector equation for the line of intersection between the two planes, you're basically solving the system. That's it. So you can solve it using Gaussian elimination or Gauss-Jordan. I need to do R2 minus 2R1, 1, 2, negative 3, 2, negative 2 times this to this 0, negative 2 times this, negative 4 added to this negative 1, negative 2 times this 6 added to this 5, negative 2 times this negative 4 added to this 4. So I can now write the system. Maybe also do minus R2 to bring it to the row echelon form. So x is equal minus 2y plus 3z plus 2, and y, that is also a leading variable. So x is leading and y is leading. If I isolate y, I get 5z minus 4. And then what do I do for z? Since my z is a free variable, I'm going to assign a parameter to that. And for parameters, we use either s or t. So I'm going to use t for this one. Okay. So what I have here, yes, I just need to get rid of the y and the z so that I only have t in it. That would be the parametric solution for a line in R3. Yes. So let's see. Z is just t, and y is 5t minus 4. I just replaced the z here by t because z is equal t. And then for x, I get minus 2y, so 5t minus 4, plus 3z, so 3t plus 2. So I get minus 10t plus 8 plus 3t plus 2. That's going to be minus 2t. Nope, it's supposed to be minus 7t plus 10. So the parametric solution becomes x is minus 7t plus 10, y is 5t minus 4, and z is just t. So this would be the set of parametric solutions for the line of intersection between the two planes. And then I can easily, from this, I can write the vector equation. X, y, z is 10 minus 4, 0, plus t times, I just need to write the coefficients of t, negative 7, 5, 1. So that x is 10 minus 7t, y is minus 4 plus 5t, and z is 0 plus 1t plus t. So this is the vector equation for the line of intersection between these two planes. So basically, the only thing I did here was to solve the system. I just solved the system. There is x here. I solved the system, and then I wrote the general parametric solution. If you remember, this is how we write the general parametric solution for a system of linear equations of two planes and in R3. So it's basically the same thing. Okay. Next example. Given this point and this plane, you have a point P0, 1, negative 1, 7, and a plane 3x minus 2y plus 5z equal 11. We want to find a vector equation of the line that passes through the point P0 and is orthogonal to the plane. So this is the situation. We have a plane and we have a point. And this point, I believe, is not in the plane. We are looking for a line that passes through this point and is orthogonal to the plane. Find a vector equation of the line that passes through the point P0 and is orthogonal to the plane. Okay, so in order to get a vector equation for such a line, I need a point, which I have, and I need a vector that is parallel to the line. But I don't have a vector parallel to the line. What I have is the normal vector for the plane. The normal vector for the plane is, if you look at the coefficients, A, B, C, that's going to be 3, minus 2, 5. But do you agree that if the line is orthogonal to the plane, and the normal vector is also orthogonal to the plane, then the vector, the normal vector for the plane and the line are parallel? Okay, so I have a line, I have a vector parallel to the line. I'm going to use that. OP0, OP is OP0 plus TV. So X, Y, Z is going to be 1 minus 1, 7 plus TV. And I'm going to use the normal vector for the plane. 3 minus 2, 5. And since it is asking us for a vector equation, we can stop here. That's a vector equation. Part B, find the point of intersection between the plane and the line. So we have a plane here, 3x minus 2y plus 5z is equal 11. That's the given plane. And we were able to find an equation for the line that passes through the point P0 and orthogonal to the plane. Do you agree that this point here, I'm going to call that P, which is the point of intersection between the line and the plane, is going to be the closest point on the plane to the given point? Because the closest point would be the point that is right beneath that, orthogonally beneath that. So if I'm able to find the point of intersection between this plane here and the line that I found, I have actually found the closest point on the plane to P0. And this is exactly what it is asking us in part B. It says find the point of intersection between the plane and the line in part A. And it says note that the point in part B is the closest point on the plane to the point P0. How do I do that? Very easy. I just need to first write down the vector the parametric equations. 1 plus 3t, that's for x. Negative 1 minus 2t, that's for y. And z is 7 plus 5t. Then I would need to replace this for x in the plane, replace this for y in the plane, and replace this for z in the plane to find t. So that is, I have to solve this. 3 times x, 1 plus 3t, minus 2 times y, minus 1 minus 2t, plus 5 times z, which is 7 plus 5t, is equal 11. If I solve this equation, there is only one unknown here, the t. I will find t. As long as I have t, as soon as I have t, I can plug it in here and get the point. Okay, so I have 3 plus 9t plus 2 plus 4t plus 35 plus 25t is equal 11. And 9 plus 4, that's 13. 13 plus 25 is 38. Am I right? 13 plus 25, that's 38t, plus 5, 40 is equal 11. That means 38t is equal minus 29. That means t is minus 29 over 38. Okay, so what is x? X is going to be 1 plus 3t. So I replace t with this. Y is minus 1 minus 2t. And z is 7 plus 5 times t, negative 29 over 38. So that point P, I'm going to use my calculator for this one. If I do 29 over 38 times 3, negative 3, plus 1, I get minus 49 over 38. Then for the next one, 29 over 38 times 2 minus 1. That is 10 over 19. Finally, if I do 29 over 38 times minus 5 plus 7, that gives me 387 over 38. So that would be the closest point. The closest point P on the plane to the given point P0. So I hope I did not make any calculation mistakes, but I showed you the method, what to do. So basically it's like this. If you have some line that passes through the point P0 and is orthogonal to the vector, to the plane, you can use the normal vector for the plane as the vector that is parallel to the line. So if this normal vector is A, B, C, then the equation of the line is going to be x, y, z is P0, X0, Y0, Z0 plus TV, ABC. So X is going to be X0 plus AT, Y is going to be Y0 plus BT, and Z is going to be Z0 plus CT. Then if you need to find the point of intersection between the plane and the line, assuming that the plane is AX plus BY plus CZ is equal D, you would just need to plug in these values into X, Y, and Z, and then solve for T. So you plug in A times X0 plus AT plus B times Y0 plus BT plus C times Z0 plus CT is equal D. You just replace X with this, Y with this, and Z with this. Then you solve this equation for T. The moment you have T, you have the point, because you can plug in back T into these equations and get the X, Y, Z of the point. Is this clear? This is B, Y0 plus BT. And this is C, Z0 plus CT is equal D. Okay, I'm going to stop here. Next class, I'm going to talk about the vector and parametric equations of a plane. For now, you can start working on the problems 1 to 12. Problems 1 to 12 is all about